My name's Daniel. I'm a lecturer here. I'm also a college fellow and I do admissions for engineering. And the idea of the little taster that I'm giving you today is to demonstrate both A, what I do in my research, and B, to give you an idea of the breadth of engineering, that it's possibly a lot bigger or wider than you may have thought. It's not just cars and bridges. So I'm going to focus basically on just the really fundamental physics of nuclear magnetic resonance. But what I work in is magnetic resonance imaging research. And most of what I do is either working with clinicians in the oncology department who are doing clinical trials for cancer research, or I'm working with people in the neurosciences department who are working on dementia. But as far as we're concerned, it's all engineering. We're looking at the fundamental physics and maths of how some of these techniques work so that we can support the clinical research that's going on in the university. So just before we begin, show of hands, who feels that they're completely comfortable with and totally understand quantum mechanics? Excellent. I'll fix that in under 15 minutes. So I'm going to cover, this is taken from a lecture that I actually give. And so it sort of gives you an idea of how I approach things. Every lecturer does things slightly differently, but generally there's some themes. So we start off by telling you what we're going to tell you, then we tell it to you, then we explain to you what we've told you, and then we give you some handouts in case your writing's illegible, or that you can't hear what I'm saying. Now, the most important letter in NMR or MRI is the R. It's the resonance. Now, resonance is a property that lots and lots of things have. For example, Kelvin has resonance. A system will resonate if it has some kind of intrinsic natural frequency associated with it, and you then provide extra energy into that system to increase the amplitude of the oscillation. So, when you sit on a swing, if you just sit on the swing, nothing happens. However, that system, that Ewan swing system, has an intrinsic frequency associated with it. If you take the swing with a person on it and you pull it back a little bit and you let go, it will swing backwards and forwards. And if it takes 1 second to swing backwards and forwards, it doesn't matter how far back you take that swing. The amplitude of the oscillation is not related to the period of the oscillation. So if you pull it back further, it doesn't take longer for you to complete one swing. You just go faster and it takes the same amount of time to complete that swing. So that length of swing with a massive U on the end of it has an intrinsic frequency associated with it, an oscillation frequency. And if you want the amplitude of that oscillation to get bigger, what you have to do is add energy to the system. How, unless you've got a friend who's going to push you, how do you add energy to your swing system to make the amplitude of the swing go higher?
Your legs.
Kick your legs. Like this. Does that work? No. What you have to do is you have to kick your legs at the resonant frequency of the swing system. When you're at the back of the swing, you kick the legs forward. And when you're at the front of the swing, you kick the legs backwards. You also have to do it at that exact point and in that order. So you have to do it in the correct phase. If you kicked your legs forwards halfway through the swing, it wouldn't work so well. If you kicked your leg forwards at the end of the swing, it wouldn't work. So you have to add energy at the same frequency as the resonant frequency of the system and in phase with its current motion. And when you do that, the amplitude of the oscillation will increase. This is called resonance. You are now resonating with the swing. This is what I've just said. This is another thing that I do in my lectures. I put up pretty pictures, I wander around, wave my arms, and talk about things, and then everybody knows that they can pay attention to me. They don't need to take notes, because what I've just said is then on the next slide, which they have as a handout. Because I'm kind, basically. So, that's what I've just said. Now, it turns out that kids on swings and protons are effectively the same thing. That when you have a proton, or an electron or a neutron, they all have a property which we call spin. It is a quantum mechanical property, and it basically has a lot of the same features as if you put a basketball on your finger and you spin it around like that, and it turns around and it's spinning about on your finger. So it's basically, and it has mathematically, we call it angular momentum, and from a mathematical perspective, it's the same as spinning a ball on your finger. It's slightly different because you can stop a ball that's spinning on your finger, or you can speed it up or slow it down. Protons, electrons, and neutrons have an amount of spin. They have an amount of mass, they have an amount of charge, they have an amount of spin. You can't chip a little bit of mass off a proton, you can't reduce a little bit of charge from the proton, and you can't reduce the amount of spin that the proton has. They are fundamental properties. And so you can't speed it up or slow it down, it just has this spin. Now, for mathematical reasons, these are called spin half particles. They don't have half a spin, it's just that when you sort of put some constants in and divide them out and put them into the equations end up being much simpler if we add them up in lots of a half rather than lots of one. So it's just a mathematical quirk. And we call all spin half particles fermions, which is a physics thing. And so protons and electrons, unlike neutrons, have charge. They have charge and they have movement. And if any of you have done any decent physics, you should know the universe is always made up of three things: charge, movement, and magnetism. And you will always have the three together. If you have charge, you add movement, you get magnetism. If you have magnetism and you have movement, you get charge. They're always there, and they're always perpendicular to each other. And so the spin is a movement with a direction. It has a charge, and so it also now has a magnetic moment. And helpfully, it looks just like the Earth. The Earth is a big ball. It's spinning around its axis, and at the top, very close to that axis of rotation, you have a magnetic field. So you've got a north pole and a south pole. Protons and electrons do exactly the same thing. At the axis at which they're spinning around, they have like they're a bar magnet with the north pole at one end of that axis and the south at the other. So the direction of spin is kind of going around that way, which is difficult to put a vector on. And so what we do is we put the vector along that axis about which it's spinning. And so the direction of the spin and then the direction of the magnetic field are parallel. But the motion, of course, is perpendicular to that direction that we give the spin. So we rarely interact with just a proton by itself. We're usually interacting with atoms. And if most atoms, when you start packing the nucleus together and you've got protons and neutrons and you're packing them all into a nice little container, like carbon-12, for example, which is the most common isotope of carbon, what happens is the spins tend to align. All the protons pair up, all the neutrons pair up, and so you've got one proton with spin in that direction and one proton with spin in that direction. You add those two together and you end up with no net spin. Now, it's a little known fact that subatomic particles are a bit racist. Now, nobody's told you that before, but just quietly, they are a bit racist. Protons will only pair up with other protons, and neutrons will only pair up with other neutrons. So, for example, in deuterium, you may think that, there's only one proton, there's only one neutron, they've got no choice. What will happen is the proton will have its spin in that direction, the neutron will have its spin in that direction, and they'll pair up. No, not subatomic particles, they will do this. And they will end up having spin 1. You have that half plus that half ends up with 1. Whereas when you get to helium, helium has 2 protons and 2 neutrons. The protons will pair up, the neutrons will pair up in opposite directions, and you'll have spin 0 for helium. So different isotopes and different atoms will have a different net nuclear spin depending on their arrangement of their protons and their neutrons. And in some cases, like the most common isotope of hydrogen, hydrogen-1, is very lonely. He can't even afford to be racist. There's no one for the proton to pair up with. It's all by itself. And so hydrogen will always have spin half because it's only got one nucleon, a proton. And likewise, there's an unstable isotope of carbon, carbon-13, and there's one left with no date for the prom. And so that will also be spin half. So despite the fact that they're very different sizes, very different weights, very different chemical properties, they both are spin half with the nuclei. So the rules for working out exactly what the spin is basically you take account of the fact that subatomic particles are a bit racist. And so if we've got an even number of neutrons and an even number of protons, they'll balance out. If you've got an odd number of either or the other, then they add up weirdly. And so you end up with things that are spin half, spin 3 halves, or integer spins. Now, we probably don't care too much about that because most of these things are fairly uncommon. And when we want to do medicine, what we're interested in is something that we've got a lot of in our body. We don't have a lot of carbon-13 kicking around inside of us. What we do have is a great deal of water, and water is H2O. So we've got 2 hydrogen atoms as ions in water for every water molecule that we have. So we've got billions and billions, possibly even trillions, of lovely little spin half particles, which are sitting there with spin and with little magnets inside them. Because when the spins line up in opposite directions, the magnets line up in opposite directions, and they cancel each other out. So why do we care about spin, and why do we care whether it's a half or a 1 or a 3/2? And that's because it tells us how many possible energy levels it can have. So if I'm a magnet and I'm in a magnetic field and I align myself to the magnetic field like a needle in a compass, that's a low energy state. If I tried to push myself in the other direction and was opposed to the magnetic field, that would be a high energy state. Now, generally things don't like being in high energy states. Everything will sort of, thanks to entropy, fall down to be the lowest energy state that it could be. But if you aligned all of your magnetic spins, all of your spins in the same direction, you'd end up creating this huge magnetic field and you'd be magnetized, and that actually contains a lot of energy. So having your spins mainly lined up parallel to each other, so you've got one magnetized in that direction, one magnetized in that direction, and no net magnetization, is a lower energy state. And when you apply an external magnetic field, only a couple of them will change state and most of them will remain opposed. But you've still got this aligned with the field and anti-aligned with the field option when they're all paired up. And the one that happens to be naturally aligned with the field is in a slightly lower energy state than the one that's paired up with it and is now anti-aligned with the field. And so now we've got two different energy states that we can be in, pointing north or pointing south effectively. Yeah, so we've got this split in energy levels, and we give a magnetic quantum number m to these two different levels. And so it looks like this. If you imagine this is sort of a graph, and that we've got, as we go along here, the magnetic field which is pointing up gets bigger and bigger and bigger. If you've got no external magnetic field, then there's no preferred direction. There is no up or down because it's relative to the field. And so there's only one energy state. If I apply a small amount of magnetic field, suddenly I've got two different energy states there, and they're a little bit further apart. And as the field that I apply gets bigger and bigger and bigger, the separation between those energy states gets larger and larger and larger. And so being opposed to the field has a very different, it requires more energy to be in that state than being aligned with the field, which is why that's up higher than the other one. Now, we were running out of letters, and so magnetic field is denoted B. And it's easy to remember because there are no B's in the words magnetic field, which doesn't happen with any other constants that we use. So now we've got two potential states that we can be in, and the separation, the difference in energy between those two states is determined by how big that magnetic field is that we're applying, which is also important. So we've got two energy states, and we want to know the difference between those two energy states. And so we have an equation for the delta E, the difference between the up state and the down state. And it's given by gamma, which is a magic number, H, which is a constant, B, which is the magnetic field strength, 2, which is a number, and pi, which is a constant. So really it comes down to whatever this gamma is, and then our magnetic field strength determines how big that distance between the two is. And the gamma is called the gyromagnetic ratio. And that's a really, really sort of specific number that's determined by what my atom is. Not just what my nucleus is, because hydrogen by itself will have one gyromagnetic ratio. Hydrogen as part of a water molecule will have a slightly different gyromagnetic ratio. Carbon-13 has an even different magnetic ratio. And so we get some information of its behavior, of not just what the nucleus is or what the atom is, but where the atom is, what molecule it's in. And that will change those two different energy levels. And always the lower energy level will contain slightly more, and that will sort of like balance. So we've got most of them paired up, but you're going to have a few more, like 1 part in 100,000, 1 part in a million, of more in the lower energy state, which is sort of balancing the applied magnetic field. But generally the distribution between the two is like, it's a Boltzmann distribution. It's more like thermodynamics than it is quantum mechanics at that point. So for a bunch of different potential isotopes that we could stick in a magnetic field, we know how many unpaired protons, how many unpaired neutrons. It gives us a net nuclear spin, and then we can see there's a range of different gyromagnetic ratios, gammas. And so hydrogen 1 in water is a nice big one at 42. Hydrogen 2 ends up with a very small. So there's a very small energy difference when you're deuterium as opposed to hydrogen. And you look down and you've got like phosphorus and carbon and things. But with carbon-13, there's not a lot of carbon-13 around. Most of the stuff that we're dealing with is carbon-12. And so the amount of signal that you will get from your average human body from carbon-13 is really small because you don't have a lot of carbon-13. Whereas with hydrogen, again, you've got this big gyromagnetic ratio and you have lots of it. And so you've got lots to play with. That's why we do our imaging with this with hydrogen because there's lots of it around in people. Now, this is where we get to the quantum mechanics bit. During the 1800s, physicists were a little bit confused. They thought that, somewhat accurately, the world is made up of objects and systems. Objects are very simple and have very few properties. Systems are very complex and have quite a lot of properties. And they looked at a clock, a wind-up clock, for example. It's clearly a system. It's got lots of moving parts, things move in different directions at different rates. There's all sorts of crazy stuff going on inside. It's clearly a system, it's quite complex. You pull the clock apart and inside you'll find a cog, just one cog. It's pretty simple. It has a diameter and a number of teeth. So we call the cog an object, which is very simple and has very few properties. And you take a lot of different objects together and you build them together in a complicated way and you can create a system which is quite complex and has a lot of properties. They were wrong. What they thought was as you got smaller and smaller, you went from, I'll do it your way around because that makes sense. You went from complex system, very large, lots of properties, and as you got smaller and smaller and smaller, they became more object-like and became more and more simple with fewer properties. But in fact, what that plot looks like is more of a U shape. That if you start off with a building like the one you're in, it's a system, it's quite complex, and you get down to a brick, which is relatively simple. And then when you start getting into atoms and subatomic particles, they actually start getting more complex again and start looking more like systems. For example, the average electric charge of your brick is 0. The average magnetic field that you would expect out of a brick is 0. The average amount of net nuclear spin that you would experience from your average brick is 0. And that's because all of these properties usually come in two different types and they usually pair up whenever they can and cancel each other out. When you get down to one proton and it's got nothing to pair with, it ends up still having properties. And some of these properties, things like spin, are what we call stochastic. They have statistics and percentages associated with them rather than fixed values. Now, to explain quantum mechanics, I present the coin. This coin can be spun like this. When it's in midair and it's spinning, is it a head coin or a tail coin? It's a stupid question. It's neither. It's both. The question itself doesn't make sense. It is a system, when measured, has a 50% chance of being heads and a 50% chance of being tails. But the act of measurement is so intrusive to that system that I will destroy that kind of behavior and leave it with only one answer. If I take a proton, which is spinning and got a magnetic moment, and I place it in an external magnetic field, when I measure it, I will measure it to have either been in the high energy or the low energy state at the point of measurement. But prior to that point, it is a system which has a 50% chance of being measured in the up state and a 50% chance of being measured in the down state. But prior to the measurement, it's effectively what we call a superposition of both states. But because it's so small, the only way that we can interact with it, the only way we can measure it, is doing things like throwing another proton at it, throwing a photon at it, throwing something at it that is so large and has so much energy it's comparable to the proton itself, which is like slapping it out of the air, and it stops behaving the way that it was and starts being more object-like in appearance. But prior to that point, it was quite happily a system that just had these probabilistic states associated with it, like Schrödinger's cat. Schrödinger's cat is often misunderstood in science fiction in that it was proposed as demonstrating how ridiculous quantum mechanics was, that it couldn't possibly work. If I have a cesium isotope, which is unstable, that has got a half-life of a certain period, let's say it's got a 5-minute half-life, that means that within any given 5-minute period, it has exactly a 50% chance of undergoing nuclear decay, the nucleus breaking apart and emitting radiation. Now, if you put an unstable cesium isotope in a box, and you put a Geiger counter in there pointing at it, and the Geiger counter was connected to a hammer, and under the hammer was a vial of poison, and then you put a cat in the box, and you closed the box so that there was absolutely no idea to know what was going on in it. In any 5-minute period, there is exactly a 50% chance that your cesium atom will have decayed, set off the Geiger counter, broken the poison, killed the cat. And so until you measure it by opening the box and looking, it is a superposition of the two possible states, meaning the cesium atom is both half decayed and half not decayed. The Geiger counter is both half clicked and not clicked. The vial of poison is half broken and half not broken, and the cat is half alive and half dead. This is clearly nonsense. Thus, quantum mechanics was wrong. But what they failed to appreciate is that quantum mechanics doesn't scale up to cats. The cesium atom is quite happy being half decayed and half not until you start interacting with it. But by the time you've added all the other elements to go through systems to objects back to systems again, everything smooths out and cats are either completely alive or completely dead. So no cats were harmed in the making of this slide. He liked being in the box. So again, I've just explained all of that and you didn't have to take notes because it's written on the same thing. So any individual particle is quite happy being the spinning coin in midair where it is a fractional combination of the possible allowable states of that particle. So what happens when we put a proton in a magnetic field is it doesn't just have these two possible states, it does something else as well. And that something else is called precession. And precession, weirdly, is not something that's unique to subatomic particles. It also happens to bicycle wheels. That if you put something that is spinning in a force field, like gravity, for example, it will have the axis about which it is spinning start to rotate slowly about the direction of that force field. This is what enables motorcycles to go around corners, or bicycles to go around corners. And I did have a wonderful demonstration where I had a bicycle wheel suspended on a pendulum. And if you turn the bicycle wheel up sideways and spun it, it then drove itself around and around and around that pendulum. It's sort of like apparently in midair. And the trick is that the top of the bicycle wheel is trying to fall down, but it's also going that way. And the combination of that and that means that it does that. And so the bicycle wheel starts to curve around. And so its axis of rotation was like that, but the axis of rotation would rotate about the vertical force field of gravity. So when you take a proton, which is a little magnet, and it's spinning, and you put it in a magnetic field, the magnetic field is applying a force that's trying to orientate that proton in the direction of the magnetic field. But the spin makes it kind of turn sideways while it's doing it, and so it does this little precession. Now it's a separate motion, and I'll try and get this to work. So this is now my proton. I've got a vertical magnetic field. Its axis of rotation is through there, and you'll see these arrows demonstrating its actual spin rotation. And then when you put it in the field, if I can get my mouse, hopefully this will work, you will see that this axis of rotation, the red line, starts doing that. Now for these ones, the velocity of the two looks quite similar. This spin is probably 10,000 times faster than this precession. The spin is going around like crazy and the precession goes quite slowly in comparison. And that's because the spin is fixed, whereas the rate of precession is determined by the strength of the magnetic field. So if I put this in a field of twice the strength, the spin stays the same, but that precession rate doubles. If I put it in half the strength of the magnetic field, the spin stays the same, but that rate of precession halves. So this is what goes on when you put a proton in a magnetic field. And I've said that, it's basically the same with bicycle wheels and stuff like that. It's very nice. Now, what gets really weird is that the frequency at which it's precessing is the Larmor frequency, which is given by omega, and it's determined by the gyromagnetic ratio and the strength of the magnetic field. Now, that's basically very similar to the energy difference between the upstate and the downstate, which is also determined by the gyromagnetic ratio and the strength of the magnetic field. So it's the rate at which it's spinning is directly proportional to the difference between its two different energy states. And the energy state, if you were trying to go, well, how much energy is that? If I had a photon with that amount of energy, what wavelength would that photon have? What would be the frequency of that photon? And it turns out that its frequency is the same frequency as that precession. And so the amount of energy that you need to give a proton to change from the upstate to the downstate is the same amount of energy that a photon has with a frequency which corresponds to the rate at which the proton is doing this. That is not at all obvious, nor is it intuitive, and it's kind of a bit weird, but it's what enables MRI to work. Because if you have a proton in hydrogen, in water, in a patient's brain, in an MRI scanner in a hospital, that proton is going to do this. And you can't see it. But what you can do is you can throw a photon at it with exactly the right frequency of energy. and it will change from being in the low energy state to the high energy state, and then it will switch back from being in the high energy state to the low energy state and re-emit that photon at a very, very, very precise frequency. So now I have a system which is a proton, which has an intrinsic frequency associated with it by being in this magnetic field. And if I add energy to the system at exactly that frequency and in phase with its current motion, it can absorb that energy and then it can re-emit that energy again. And so I can make that proton resonate in the magnetic field by throwing photons of electromagnetic radio frequency energy at it. And so that's why your proton in an MRI scanner is resonating. It's doing exactly the same thing as when you sit on a swing and kick your legs. It will absorb a specific frequency of energy and it will emit a specific frequency of energy. And then we just need to tune our antenna to be precisely that frequency, and we can measure the behavior of protons in water inside a living body. And by fiddling with it in clever ways and changing the frequencies and changing the magnetic fields, we can pull information out of the system which tells us information about the chemistry and the thermodynamics of the system, so that we get what we call image contrast, so that we can tell the difference between tumour and healthy tissue, that we can tell the difference between damaged brain tissue and healthy brain tissue, that white matter and grey matter in the brains looks different, that lung and muscle and kidney and liver all look different, because they have a different chemical and thermodynamic environment which changes this behavior of a proton in a magnetic field. Because the gyromagnetic ratio changes really subtly as you move around, and the environment and the thermodynamics change subtly, changing the magnetic field and changing the resonant frequencies. And so just by taking a kid on a swing and a coin, you can work your way through up to medical imaging and working with clinical trials. And again, this is basically what I've just said. It works nicely. And so you change between the up and the down state by absorbing and emitting photons of a particular frequency of the quantum description. So what you have is a bunch of protons sitting there minding their own business. They don't care which way's up and which way's down. You apply a magnetic field, and now suddenly they've got these alignments into preferred directions, about half up and about half down. And when you add them all together, and they're all spinning around, you end up that it looks slightly magnetized. But this direction of magnetization is made up by billions of spins all in different directions. And that, in record time, is how MRI works based on quantum mechanics, linking in bicycles and coins and swings. So if anybody's got any questions, I'll be more than happy to try and answer them for you. Thank you very much. Questions? Criticisms, comments, advice? I'm open to everything. No. All right, you can leave. Enjoy your day. If you want to come down and talk to me about anything, please do so.